Good morning, dear students. My name is Ferhan Mazher, and today is 1st of May 2021. Today we are studying the subject of physics. This is O Levels Physics 5054. Today we have set our hearts to solve October-November 2019 paper. And the number of the paper is 2-2. This is a theory paper and this belongs from the zone 2. Today we have set our hearts to solve it section B. Section A we have already solved. It's in my YouTube channel. You can find it. So let's start today's paper. We are going to attempt the section B, which starts from the question number 9. Okay, so the first question coming up on your screen. Let me increase the size so you can see the thing. So here we go. Question number 8, figure 8.1 shows an elastic rope bungee. The unstretched length of the rope is 0.80 meters. So L naught, which is 0.80 meter. Our student uses the hook. The unstretched length of the rope is 0.80 meter. The student uses the hook at one end to suspend the rope from a shelf and hangs an empty paint can of 0.70 kg from the other end. The rope stretches to a length of 0.97 meter, but does not exceed its limit of proportionality. Explain what is meant by the limit of proportionality. A very famous, frequently asked question, that what is meant by the limit of proportionality. So let's check what I have written. Limit of proportionality basically is on the extension load graph. It's a point. On extension load graph, it's a point up till which the extension and the load, they are directly proportional to each other. The extension load graph up till that point is a straight line. But after that point, the extension and the load, they are no more directly proportional to each other. The graph, extension load graph, becomes a curve. So that point is known as the limit of proportionality. Let me show you my answer. Here we have load after which extension and load are no more directly proportional to each other is known as limit of proportionality. This is the other definition which I load after which extension and load are no more directly proportional to each other is known as limit of proportionality. So let's move to the the marking scheme. Okay, so marking scheme is showing up on your screen. Let me increase the size. Now it's good. Where or when extension is not directly proportional to the load, tension or force applied. Point, actual definition is point where extension stops being directly proportional to load or tension or the force. So remember, this is a point on the extension load graph beyond which the load and extension, they are no more directly proportional to each other. So it's a 1-mark question. Hopefully you will be able to do this. Okay, so now let's move to the next. He says, state what is meant by mass. 1-mark question. And what is meant by weight. 2-mark question. Mass is the amount of matter in a body, and its SI unit is kg. Whereas the weight, it is the force applied or pull of a body for example, if we are talking about the weight on Earth, then it will be the pull of the Earth on a body when that body is in the gravitational field of the Earth. So it's the force exerted by a body on another body due to the gravity. So the unit of the weight is like a force, its unit is Newton. And you can find it by the formula W is equals to mg. You see these 2-3 marks, they are easy. They are basic physics. So let me show you my answer. I have written this answer and then we will work. Then we will check the marking scheme. Okay, so mass is the amount of substance in a body. Its SI unit is kg. Weight, it is the gravitational pull experienced by an object in a gravitational field. Its SI unit is Newton. The formula, the formula in the next part is going to ask you a question on the formula. Let's check first of all the marking scheme. The marking scheme says the amount of matter in a body or a measure of the inertia of a body. Mass is also the measure of inertia. And for weight, he says force on a body in a gravitational field. So our answers are right. So let's move back to the question. Next question. He says the gravitational field strength is 10 Newton per kg. Calculate the weight of the empty can. Its weight is given. Sorry, its mass is given. So its mass is given. You simply have to apply the formula W is equal to mg. And very easily you can find the weight. And in the next part, he says for the rope, calculate the value of the load divided by extension. So we will do these both parts. Okay. So let's go to my work. I've done this. Let me show you. So weight is W equals to mg. W is equal to 0.70 kg multiplied 10. So weight will be 7 Newton. Simple 1 mark numeric. Okay, so the next part. Here you have to find out the ratio of load to the extension. So the unstretched length is 0.80 meter. And when you hung that can, the length became 0.97 meter. So the extension is L minus L naught. 0.97 meter minus 0.80 meter. So the extension will be 0.17 meter. Now the load divided by extension, the load is 7 Newton and the extension is 0.17 meter. So your final answer will be 41.18 Newton per meter. 41.18 Newton per meter. So that is the load ratio extension. So it's a different question. Okay. So let's check the marking scheme. What the marking scheme has to say. So C part is showing up on your screen as 7 Newton and then 41 Newton per meter. 40. So our answer is also 41 Newton per meter. So that our answers are right. You can see the marking scheme. Okay, let's go to the questions here. Okay, so we are going to the D part. And the D part is showing up on the screen now. The student repeatedly pours small volumes of paint into the can. When there is 2.5 exponent minus 3 meter cube of the paint in the can, the total length of the rope is 1.70 meter. This is where the rope reaches the limit of proportionality. Determine the mass of the paint in the can. So I know, now I know the volume of the paint, I know that. And I know the total length of the rope. So from the length of the rope, I can find out the extension in the rope And from extension, I can find out the weight of that can with the liquid, with the paint. And from the weight of the can with the paint, I will subtract the weight of the empty can, and I will find, by doing that, I will be able to find out the weight of the paint. And from the weight of the paint, I can find out the mass of the paint. So let me show you how I have done this. So here we go. Okay. So now the L naught is 0.80 meter. That's the unstretched length. The length right now with the paint in the can, the length of the rope is 1.70 meter. Extension is equals to L minus L naught. That will be 1.70 minus 0.80 equals to 0.9 meters. So the extension is 0.9 meter. I know the ratio of the load to the extension, that is 41.18. The value of the load I want to find out, the extension is 0.9. So load divided by 0.9 equals to 41.18. So load will be equals to 41.18 by 0.9. So load will be 37.062 Newton. So now I know this is the load of the, the can with the paint. That's the weight of that can and the load. So let's convert this into the mass. Mass will be weight divided by G. So 37.062 divided by 10. So that will be 3.7 kg. So the mass of the can filled with the paint is 3.7 kg. So from that, subtract the mass of the empty can. That will be 3.7 minus 0.7, and you will get the mass of the paint only. So that will be 3 kg. So a little higher level question. I hope you have understood. Let's check the marking scheme. Our final answer is 3 kg. Paint of the mass of the paint will be 3 kg. So let's check. Let's check what the marking scheme says. And the marking scheme is showing up on your screen. So the marking scheme says 3 kg. The final answer we are getting is 3 kg. The final answer of the question number 8D, first part, is 3 kg. Hopefully you have understood. Let's go back to the question. He says, the student continues to pour paint into the can until there is a volume of 5 expo minus 3 meter cube. In it, he notices that the elastic rope becomes harder to stretch after the limit of proportionality. He plots a graph of the total length of the rope against the volume of the paint added. On the figure 8.2, sketch the length volume graph for the range 0 to 5.0 into 10 to the power minus 3. So this is the limit of proportionality. So up to this point, let me show you the graph. So this is the limit of proportionality. So up till this point, the graph has to be sketch the length volume graph for the range 0 to 5. So up till this point, the graph has to be, a straight line. The length and the volume, the graph should be a straight line. So let me show you. I have done this. Okay. So question number 9, question number 8, D, second D part. So here you see, up till this point, the graph will be a straight line. graph will be a straight line. Okay. Now, let's go back. This is the question, okay? Up till this point, you have to draw a graph. This graph should be a straight line. Let me check the mark. So these are the two approaches which we have shown. For question number 8D, first part, we have gone with this approach, this one. Okay. Question number 8D, second part, straight line to mark location of y-intercept. And you see, curve of changing chain gradient beyond mark point. Intercepts not to be labeled. Okay. So you see, we made a mistake here. So let me show very important mistake. Let me take it. So let me open it in the paint. I can show you what's the mistake we have made. So here we go. You see, because this is not extension. This is not extension, this is length. So so what I have to do, this line here, this line should not be here. This line is a straight line, no doubt, but this cannot pass through the origin because on the y-axis you have the length. So if on the y-axis you have the length, then the graph cannot pass through the origin. Because when there is no load, the graph cannot pass, the length of the rope will not be 0. And when there is no load, the length of the rope will not be 0. So the graph cannot pass through the origin. Origin means 0, 0, which means that when the load is 0, when the volume of the paint is 0, the length of the rope is also 0, which is not possible. So you see, my dear student, this is a common mistake which a normal student will make. And I was trying to show you that this is the mistake which will be happening. Okay. Now, another mistake which can happen, beyond this point, you know, he told you that this will become harder to extend. After this point, what happened? The graph become harder to extend. Okay, so the graph cannot go up. So this is a common mistake which normally a student is going to do. That when he will draw a length and volume graph, he will pass his straight line graph through the origin. You are not supposed to pass it through the origin because when there will be no paint in the can, even when there is no load on the rope will have a certain length. So very famous mistake. I was just trying to show you this. Okay, so this is done. Okay, so next part is the student suddenly removes the can from the end of the stretched rope, and it is as it contracts, the rope jumps into the air. State the energy change that is taking place in the rope as it contracts and jumps into the air. It's a 2-mark question. Okay, so let me show you my answer. So first of all, let's bring it here. Okay, so this is the correct graph. A very famous mistake. You know, if this is extension load graph, this line will go through the origin. Okay. But this is length, so it cannot. Okay, so next part is now. Here we go. So the elastic energy will be converted into kinetic energy and gravitational potential energy. So see, when you release it, it has the was stretched. When the rope is stretched and you release it, what happened? That its elastic potential energy will convert into the kinetic energy, and because the rope jumped upward, so it will also gain some gravity. Let's check the marking scheme. The marking scheme. From elastic potential energy or string energy to kinetic energy or to the gravitational potential energy. It's very simple. Okay. So you have to tell the different forms of energy. It will have the elastic potential energy, and that will convert into the kinetic energy and the gravitational energy. Hopefully you have understood. So that's it. This was the question number 8, a very important question. And the most important thing was that when we draw this graph is between the length and the volume of the bed. When the volume will be 0, the length of the rope will not be 0. So many students will fall for this mistake, because we are preoccupied with the extension load graph. On the y-axis, if I have extension, then on the 0 load, there is 0 extension. But here we don't have extension. Here we have the length. So remember this difference. Okay. So we are moving to the next part. Next part is, that's question number 9. Here we go. We have the question number 9. So figure 9.1 shows a boiling liquid at its boiling point trapped in a cylinder by a piston. So here we have a power supply, we have an electric heater, here we have a liquid. It's being boiled by this heater, and this heat, the boiling liquid is converting into gas. That gas will push this piston upward. From outside, the weight of the piston is acting downward, plus the atmospheric pressure is pushing it downward. And this gas, because it has stopped its air, so it means the pressure of this gas and the pressure of the atmosphere, and that is equal to each other. So that's why this piston is stable here. He says there is an electric heater in the liquid which is connected to the power supply. So we are basically talking about this electric heater. The thermal energy produced by the heater gradually turns the boiling liquid into a gas. State what is meant by a boiling point. Boiling point is a specific temperature at 1 atmospheric pressure when a liquid will convert into gas. The temperature at which, the specific temperature at which, at 1 atmospheric pressure, a liquid will convert into gas. The state will change. That temperature is known as boiling point. Let me show you my answer. I have written this answer. So there we go. Next question. Specific temperature at 1 atmospheric pressure on which a liquid converts into gas. That temperature will be known as the boiling point of that liquid or that gas. So hopefully you have understood. It's a very famous question and people make mistake in writing this definition. Okay, so now we go to question number 9. Okay. He says the temperature at which a liquid becomes a gas or vapor. That temperature is known as the boiling point. So hopefully you understand it's a 2-mark definition. Let's go to the next part. Explain in terms of molecules why it is necessary to supply energy in order to turn a liquid boiling point into the gas. So why do we have to supply energy? We have to supply energy because we have to break when the liquid is converting into gas and the temperature is already boiling point. Then you are providing still the energy, and where that energy is used. that energy is used to break the intermolecular bonds completely, to overcome the intermolecular forces, and to move the molecules of the liquid away from each other. And another very important thing, you have atmospheric push on that liquid. So you have to overcome that atmospheric push also to go out of the body of the liquid into the air. So for these things, the energy is needed. We call that latent heat of vaporization. So you have to provide the latent heat of vaporization. So hopefully you understand. It's a 3-mark question, very important, and only 4 lines are given. So means you have to be very specific your answer. Okay, so let's see what the answer I have written. Energy is used to break the intermolecular bonds, overcome intermolecular forces, move molecules apart, and push atmospheric pressure. So the atmospheric pressure, we're trying to keep those liquid, the gas molecules inside that body. But then you have to push, or you have to work against the atmospheric pressure. Let's check the marks. He says forces between the molecules of the liquid bonds mentioned move molecules apart or overcome forces between the molecules, work done against the forces, or gain molecular potential energy. So the marking scheme is in front of you. You can write a better answer, I think. And we have also written 3 mark. It's a 3-mark question. C part. In order to determine the power of electric heater, 2 meters are connected into the circuit. 1 meter measures the current in the heater and the other meter measures the potential difference across it. On the circuit in the figure 9.1, draw symbols to show the 2 meters used and where they are connected. Okay. So ammeter, remember the ammeter is always connected in series with the, for example, here you are working with the heater. So the ammeter will be connected in series with the heater, and the voltmeter should be connected parallel to the heater. So let me show you my work. I have done this. I have drawn the diagram. Here we go. You see here, I have shown an ammeter which is connected in series with the, and here I have shown a voltmeter which is connected in parallel to the heater. So this is what you have to do. Hopefully you understand. Okay. Let's check the marking scheme, what the marking scheme has to say. Ammeter symbol in series and the voltmeter symbol across the heater power supply. Okay, so let's do the next part. Yep. The current in the heater is 2.01 ampere and the potential difference across it is 6 volt. Calculate the power of the heater. You know the power formula, electric power, P is equals to IV. P is equals to IV. So power, I can find the current values given, the voltage values given. Simply you have to put those values. Then the next part is calculate the thermal energy supplied to the liquid by the heater in 1 minute. Energy, it will be power multiplied time, but the time should be in seconds. Let me show you how I have done this. Okay. So question number 9, D first part, power is equal to IV. Power is equal to 2 ampere multiplied 6 volt and 12 watt will be the answer. The question number 9D second part is you have to calculate the thermal energy, the electric energy which is used or the thermal energy which is produced. They can be found by the formula power multiplied time. The power is 12 watt and the time is 1 minute. I will convert the minutes into seconds. That will be 1 multiplied by 60. So you will have 12 into 1 into 60. That's 720 joules. So the thermal energy produced will be 720 joules. Let me show you the marking scheme. Then we will see. So you can see marking scheme 12 watt and 720 joules. So our answers are right. Okay. So I think our answers are right. Okay. So let's go. The next question. The next part is, he says, the specific latent heat of vaporization of the liquid is 9 exponent 5 joules per kg. Calculate the mass of the liquid that vaporizes every minute. Okay. So I can use the formula, heat is equals to ml, because the state change taking place. Heat equals to m multiply ml. Heat means the heat you supply, and m means the mass which we want to find out, and l means the specific latent heat of vaporization. 2 marks numerical, very easy. It's a famous formula. The famous number. Heat is equal to m multiply l. The third part I'm doing. The heat is 720, and the m I want to find out. The L value is 9 expo 5 joules per kg. So this 9 expo 5 will go on the other side. It will divide on the other side. So you will have 720 divided by 9 expo 5. So you will have 8. So the final answer will be, 8 expo minus 4 kg. And if you multiply it with the 1000 to convert this into grams, so your final answer will be on the calculator 0.8 gram. So 0.8 gram of that liquid will be converted. 0.80 gram of that liquid will be converted into gas. Let me check them out. Important numerical. 0.80 gram, or in kg it was 8 expo minus 4 kg. 0.80 gram is the answer. And here the 8 expo minus 4 kg. In kg it will be 8 expo minus 4. In grams it will be simply 0.80 gram. So this much liquid will be converted into gas. Okay, then we have question number, the next one. So it's a 2-mark question. The piston is free to move in the cylinder. As the liquid boils, the piston is pushed upwards in the cylinder at a constant speed. The volume occupied by the gas just above the liquid increases. Discuss whether the upward force on the piston changes as the piston moves upward at constant speed. Okay. This word is very, it's a constant speed. When the piston is moving upward with the constant speed, it means that the resultant force is 0. It means if the piston is moving upward with a constant speed, it means that the acceleration is 0. It means that the resultant force is 0. How are you getting the resultant force? Resultant force, the weight and the atmospheric pressure is acting downward, and the gas pressure which is inside the cylinder, that is acting upward. It's applying force in the upward direction. This means that the upward force and the downward force, they are equal to each other. That's why the resultant force is 0. And that's why the piston is moving with a constant speed. And during this whole process, the weight of the piston and the atmospheric pressure, they are acting downward. They are producing the force in the downward direction. They do not change. They do not change. So it means the upward force is also not changing. It's just a little heavy question. Let me show you my answer. I have written this answer also. Upward force is equal to weight. So because piston is moving upward at constant speed, so resultant force is 0. It means throughout upward force remained equal to weight, or it means upward force is not. Upward force is equal to the atmospheric pressure, the push of the atmospheric pressure, and the weight. I just wrote here the weight, but there is also a push of atmospheric pressure. Mention that also in your answer. So let's check the marking scheme. What the marking scheme has to say about this part. He says upward force does not change. Upward force does not change. 1 mark for this. Always equals to the weight of the piston plus the force due to the atmospheric pressure, or no resultant force of piston is not exerted. So in my answer, when I wrote, I only mentioned the weight, but in my description, I'm telling you that also mention that you have to overcome the force which is exerted in the downward direction by the atmospheric pressure. So hopefully you have understood this. This answer is also a little tricky one. 2 mark question. So let's go to the next question. So question number 9 is done. Now we are moving to the question number 10. Here we go. A 2 mark question. All the isotopes of the gas radon are radioactive. State one similarity and one difference between the nuclei of the 2 different isotopes of the radon. Similarity between the isotopes is that they have the same number of protons in them. They have the same number of protons in their nucleus. And the difference is that they have different number of neutrons in their nucleus, or you can say that the nucleon number is different from each other. That's the similarity and that's the difference. Let me show you my answer. I have written this answer. Okay. So they have the same number of protons. They have different nucleon numbers. Okay, so that's the next part. The isotope radon 222 decays by alpha particle emission to an isotope of polonium PO. The proton number, atomic number of the polonium is 84. Determine the number of neutrons in an atom of the polonium isotope. Little tricky question. You know, I know the mass number of the radon, and I know the, this is the, I know the isotope radon 222 decays by an alpha particle emission to an isotope of polonium, and this is the mass number of radon given, and the proton number of the polonium is also given 84. And another information, very important information we have, is that the alpha decay happened. An alpha particle is given out. So I know the daughter nucleus, I know the parent nucleus, and I know that alpha particle is given up. So the question on me is determine the number of neutrons in an atom of the polonium isotope. So let me show you how I have done this. It's a little tricky question. It's a 2 mark question, and let me show you how I did this. Okay. So here we have on the screen radon, and I don't know what is proton number, and I don't know what's the mass number of the polonium. I only know that an alpha particle was given. You see, when an alpha particle is given out, the proton number of the daughter nucleus is 2 less than the proton number of the parent nucleus. So it means if this is 84, it is given that it's 84. And the alpha particle is this, its proton number is 2, so add them 86, so the radon's proton number should be 86, and the mass number of the radon is given, that was 222. And whenever an alpha particle decay happens, the daughter nucleus mass number will be 4 less than the mass number of the parent nucleus. So the polonium's mass will be 4 less than the whatever is the mass there. 222 minus 4, that will be 218. So you see, this is how I have written this equation. And so the question on us was, what is the neutrons? How many neutrons are there in the polonium? So the mass number is 218, or we call it the nucleon number. The nucleon number is 218 and its proton number is 84. From the nucleon number, subtract the proton number 134. So there are 134 neutrons in the polonium. Then the question was number of protons in the radon. Number of protons will be 86. So these are the first and the second part of the question number 10b. It's a little tricky one. It's not a straightforward question. So let's check the marking scheme. We are done with the question number 10b, first and second part. Okay, so here on the screen, showing you nucleon number will be 218, and it will be 134, the number of neutrons, and proton number will be 86. So I hope that you have understood that how I have done this. I wrote an equation, and before going into solving the questions, I completed that equation. Okay. So let's move to the next part. Determine the protons of in an atom of radon. We are done with this. Now we are here. Describe how a neutral atom of helium differs from an alpha particle. In a neutral atom of helium, you also have electrons which are orbiting. So there will be 2 electrons orbiting around the nucleus of the helium atom. And it's whereas in the alpha particle, you only have the nucleus. You don't have any kind of electrons around it. Alpha particle is like the nucleus of helium without any kind of electrons. So that's the difference between them. So let me show you. I have written also the answer. Okay. Neutral atom of helium will have 2 electrons orbiting around its nucleus. The alpha particle don't have electrons. Okay, so that's the difference. Very simple question. It's a straightforward, simple question. He says helium atom has 2 electrons in orbit around the nucleus. I hope you have understood. This was easy question. This part was easy. Now, here we go. In an experiment to collect a small quantity of helium, a sample of radon 222 is enclosed in an inner glass tube, which has a very thin wall. Figure 10.1 shows that this tube is placed inside a container that is initially evacuated. So here you have a seal. Here we have inner glass. This is the inner glass tube, and this is the container. And this inner glass tube has radon 222, and this container has vacuum in it. Both the container and the inner glass tube are sealed. As the radon 222 decays, alpha particles pass through the thin wall of the inner glass tube. Okay, so here the alpha particles are being given out. So they pass through this thin glass tube and they come here in this vacuum. He says, the question is, both the container and the inner glass tube are sealed. As the radon 222 decays, alpha particles pass through the thin wall of the inner glass tube. Figure 10.2 shows how the total number of alpha particles produced by the radioactive decay of the radon 222 changes as time passes. So here we have the figure 10.2. In the figure 10 point, number of the alpha particles produced. So here we have the time. Time is given in days. on the y-axis, we have the number of alpha particles produced. Okay. Use the figure 10.2 to determine the number of alpha particles produced in 7.6 days. 7.6. So, you know, this is 8 point. So 7 is basically here, you know, this is 7. This is not 7, sorry. Here I will have 9. The 7 will be here. 7 will be here. Okay, 7.6 will be 7.2, 7.4, 7.6. So where the cursor is right now, that will be 7.6. So from here you go up to the graph. When you touch the graph, then from there you go to the y-axis. And there you will find the number of alpha particles. Hopefully you have understood. So this is a 1 mark question, and I've done this. Let me show you. So from the figure 10.2, this number is coming from that graph. That is 2.1 x power 10. 2.1 x power 10 is the answer. This is coming from the graph. Okay. So let's check the marking scheme also. The marking scheme has to say, the marking scheme says 2.1 x power 10 alpha particles. This is coming from that graph, very simple. Okay. Now, initially, there are 2.8 x power 10 atoms of radon 222 in the inner glass tube. As each radon 222 atom decays, it produces an alpha particle. So calculate the number of radon atoms that remained after 7.6 days. Okay. So number of alpha particles shows the number of radon nuclei which has decayed. So how many are left? So the number of alpha particles at 7.6 after 7.6 days, that alpha particle actually shows the number of radon nuclei which has already decayed. So I know the initial value of those number of atoms, and from there subtract this one and you will get. Let me show you. This is a little tricky question, a little tricky. Okay. So when we started the experiment, the number of atoms of the radon were 2.8 x power 10. And now, because I know that the alpha particles given out, they are 2.1 x power 10. So it means the radon nuclei which has decayed, they are also 2.1 into 10 to the power 10. So subtract them, take 10 raised by 10 common, 2.8 minus 2.1, that will be 0.7 into 10 to the power 10. So I will convert it into the standard form, that will be 7 x power 9. So how many radon nuclei are still there? 7 x power 9. A little tricky question. So let's check the mark scheme to say 7 x power 9. Our answer is 7 x power 9. 7 x power 9. 7 x power 9. So this is our answer. 7 x power 9. So our answer is right. Okay, so let's move to the next question. Okay, so we are done with this part. Now, this part. Using the number of radon 2222 atoms present initially and the number of present after 7.6 days, calculate the half-life of radon 222. Okay, it's a 3-mark question. You can see I've done this. Let me show you and I will try to explain that also to you. Okay, so here we go. So here, at the start, you have 2.8 x power 10. When 1 half-life has passed, 2.8 x power 10 divided by 2, that will be 1.4 x power 10. And then another half-life would have passed, so you will have 7 x power 9. So we have this much left. So it means that 2 half-lives have passed. So 2 multiply half-life equals to 7.6. Half-life is equal to 7.6 divided by 2. So that will be 3.8 days. 3.8 days. It means one half-life is 3.8 days. Very tricky question. Okay. So try to understand this. It's a little tricky question. This calculation is easy, but not easy. Okay. Hopefully you have understood. So let's check the marking scheme. What the marking scheme has to say. It says 3.8 days, half-life, 2 half-lives, 3.8 days is the final answer. Okay, let's go. Let's go back to the questions. It says the alpha particle becomes helium atoms which are collected in the vacuum shown in the figure 10.1. Explain in terms of properties of alpha particles why the wall of the inner glass tube must be extremely thin. The wall should be extremely thin because the alpha particles, they have very low penetration power. They can only penetrate like 4 to 5 centimeters in air. They cannot pass through a paper. So their penetration power is very low. So the glass should be very thin, extremely thin, so that the alpha particles can pass through it. And the next question, let's do this next question, then we will see check much I have written. In some parts of the world, radon 222 accumulates in the air, in the buildings, and in this is breathed in by the people. Explain why the presence of an alpha emitter in the lungs is particularly hazardous. If you have taken a source of alpha particle inside your body, then why would it be dangerous? The alpha particles' ionizing ability is very strong. When they travel, they ionize the atoms which come in their path. So when they ionize the particles which come into their path, that is the dangerous thing. So when this is happening inside your body, they are ionizing the atoms in your body that cause mutation. And your cells will be mutated, and that can lead to cancer, tumor and cancer. So that's the hazard with it. So let's check what I have written as an answer. Here we go. Okay, so penetration power of the alpha particles is very weak. So thin glass must be used to allow the alpha particles to come out of the inner glass. Alpha particles have very strong ionizing ability. This can cause mutation of cells. That is the dangerous. That is the danger of the alpha particles. Okay, let's check the marking scheme. These are the last two parts. Alpha particles are very weakly penetrating, strongly ionizing. Ionization causes cell mutation and cancer. So hopefully you are done. So my dear students, we are done with this question number 10, and this is the end of this paper. So today in this video, we have done how much? We have done, let me come back to that paper. Okay, so here we go. We have done today, my dear students, October, November 2019 to paper. And we have done this in this video, the section B of this paper that includes question number 8, question number 9, and question number 10. And I've tried my best so that you can understand these questions and these concepts and some difficulty. I've tried to make them easy for you. If this video is helpful to you, kindly don't forget to subscribe to my YouTube channel. If these videos are helpful to you, also suggest these videos to your friends. I will request you to, if you have any kind of comment, feel free to comment on my video. And I also like my video. So because when you comment on it and when you like that video and when you subscribe to my channel, these are like a booster for me, and I will be able to do this work So don't forget to do this. So thank you very much, everybody, and have a good day, and God bless you all.